In this lesson, we are going to learn an application of Taylor polynomials to approximating functions. So suppose we know that a function f of x is equal to the sum of its Taylor series at a point x equals a. This means that f of x is equal to the sum from n equals 0 to infinity, the nth derivative at a over n factorial times x minus a to the n. And if we know that the function f of x is equal to this sum, how might we estimate the function? Well, one thing we could do is just take a partial sum. So we could say, well, f of x is going to be about equal to a sum from I equals 1 to n, ith derivative at a over I factorial, x minus a to the I. In other words, what this is just saying is we could just take f of a plus f prime of a times x minus a up to some value of n, nth derivative at a over n factorial times x minus a to the n. As in, we can approximate f of x using a polynomial. This is called a Taylor polynomial. Its notation is capital T sub n of x. Okay, and just to point out that you've actually already done this, we just didn't call it this. What if n is equal to 1? What is the estimate in this case? Now, if n equals 1, we just have these first two terms, and we say that f of x is about equal to f of a plus f prime of a times x minus a. That is the linearization of f of x at x equals a, i.e. the tangent line to your function at x equals a. Now, in general, the fact that you allow yourself to use different values for a, if you approximate a function f of x using a Taylor polynomial at a, this is a reasonably good approximation if you are inputting values into that function that are close to a. So you could use a Maclaurin series if the thing you want to estimate is near 0, but if you go far from 0, it might not be as good of an estimate. It might be wise to center your Taylor series at a different value. So here we're going to illustrate that point. So suppose you want to approximate the function e to the x. So we're going to find the following Taylor polynomials, and we're going to use them to estimate e to the 0.2 and e to the third. And as I said, this Maclaurin series is centered at 0, so it's going to do a better job approximating things closer to 0, which means that the approximation of e to the 0.2 will probably become more accurate more quickly than the approximation of e to the third. So first of all, the second degree Taylor polynomial will be 1 plus x squared over 2 factorial. And if we estimate e to the 0.2 by plugging 0.2 into this, we get 1 plus 0.2 plus 0.2 squared over 2 factorial, which is equal to 1.22 and then a whole bunch of zeros. And notice how even just with a second degree polynomial, we already have these first 3 digits matching. Whereas when we estimate e to the third using this Taylor polynomial, that's 1 plus 3 squared over 2 factorial, which is 8.5. That's pretty far off from the actual value of e to the third, which is 20.0855. So the 8th degree Taylor polynomial probably is going to do a much better job, but the question is how much better. So that'd be 1 plus x squared over 2 factorial plus x to the third over 3 factorial, etc., up to x to the 8th over 8 factorial. And plugging in 0.2 for x into this approximation, it's about equal to t8 of 0.2. And that is approximately equal to 1.221403, which is totally spot on to what estimate the calculator gave me. And then when you estimate e to the third using this Taylor polynomial with 3 plugged in, you get about 20.009152, which is closer to 20.08, but still this is completely accurate, whereas this one will still need some work. So the point is if the value that you're estimating is near 0, you could use a Maclaurin polynomial. But if you want to estimate something nearer to a different number, say 3, it might work better to use a different point for your center. All right, so let's find a Taylor polynomial for f of x equals inverse tangent. So the general Taylor polynomial formula, T3 of x, will be f of a plus f prime of a times x minus a plus the second derivative at a, x minus a squared over 2 factorial, plus the third derivative at a over 3 factorial, x minus a to the third. So we have a equals 1. So f of 1 will equal inverse tangent of 1, which is pi quarters. F prime of x is 1 over 1 plus x squared. So f prime of 1 is going to be a half. The second derivative, you can think about this as the derivative of 1 plus x squared to the negative first. Well, that will be negative 2x over 1 plus x squared to the second. And so inputting 1 into that, we have negative 2 over 4, which is negative 1/2. And I'll be honest, for the third derivative, I actually used Wolfram alpha because I just thought it was going to get too tedious. So just tell me what your derivatives are. I don't have to get too tedious. Use things like Wolfram alpha to check your answer because you're going to have to use the quotient rule here. That is 6x squared minus 2 over 1 plus x squared to the third. So the third derivative at 1 will be 6 minus 2 over 2 to the third. So that's 4 over 8, which is 1/2. And so our third degree Taylor polynomial will be pi quarters plus 1/2 times x minus 1 minus a half over 2 factorial times x minus 1 to the second plus 1/2 over 3 factorial times x minus 1 to the third. Now the question, this is kind of bad math grammar. You really shouldn't leave fractions within fractions. So 1/2 over 2 factorial, well, to simplify that, you multiply by 1 over 2 factorial, 1 over 2 factorial. The point being that 2 factorial goes in the bottom, the denominator with that 2, not the numerator. So this is pi quarters plus 1/2 times x minus 1 minus 1 over 2 times 2 factorial, x minus 1 squared plus 1 over 2 times 3 factorial, x minus 1 cubed. So there is the third degree Taylor polynomial, and this would be good for approximating arctan at points that are close to 1. So an obvious question to ask if we are using approximations is, if we use a Taylor polynomial to estimate a function, how good is our approximation, and how large do we need to take that n to be to achieve a certain desired accuracy? And to answer this, we have to look at the remainder. And though the remainder is found by taking the function minus the approximation and taking the absolute value. And there are 3 possible ways that you could find this error. You could actually, if you have specific functions for f of x and tn, you could graph this function and use that to estimate the error. If you have an alternating series, you could use the alternating series test to find the remainder. Or you can use Taylor's inequality, and this one is the most general, as in it will work more frequently. So that says that the absolute value of the remainder is less than or equal to some constant m over n plus 1 factorial multiplied by x minus a to the n plus 1. So in this case, you find m by looking at the n plus first derivative's absolute value and trying to figure out an upper bound for that. So a number that is always less than or equal to. All right, so let's use this. Let's approximate the function f of x equals x to the 2/3 by a Taylor polynomial with degree n equals 3 at 1. And then we're going to use Taylor's inequality to estimate the accuracy when x is between 0.8 and 1.2. Okay, so first let's find the Taylor polynomial. So your function f of x is x to the 2/3, and f of 1 will be 1. The derivative is 2/3 x to the negative 1/3. Plugging in 1 there, we get 2/3. The second derivative is negative 2/9 times x to the negative 4/3. So the second derivative at 1 is negative 2/9. And the third derivative is 8 over 27 times x to the negative 7/3. And so inputting 1 there, the third derivative at 1 will be 8/27. So our Taylor polynomial, T3 of x, will be 1 plus 2/3 times x minus 1 minus 2/9 times 1 over 2 factorial x minus 1 to the second plus 8 over 27 times 1 over 3 factorial x minus 1 to the third. So simplifying slightly, that gives us 1 plus 2/3 x minus 1. 2 factorial is just 2, so those 2's cancel, giving us negative 1/9 x minus 1 squared. And 3 factorial is 3 times 2 times 1. So that 2 can cancel with that 8, giving you 4 over 27 times 3, which is 81, x minus 1 cubed. So there is the third degree Taylor polynomial. Now we're going to use Taylor's inequality to estimate the accuracy of this approximation. So Taylor's inequality says that the absolute value of the remainder is less than or equal to some m over n plus 1 factorial times x minus a to the n plus 1. Okay, so let's figure out, first of all, we know that we are using a third degree Taylor polynomial, so we have n equals 3, so plug that in. The remainder, when you have a Taylor polynomial of degree 3, will be less than or equal to m over 4 factorial times x minus a. And actually, we even know that a is equal to 1, so let's plug that in. X minus 1 to the 4th. Okay. Now, the next thing to do is to figure out what is m. So m is a number such that the absolute value of the n plus first derivative is less than or equal to this m on the interval in question. So we need to figure out what the fourth derivative is. So the fourth derivative is negative 56 over 81x to the negative 10 thirds. And so therefore the absolute value of the fourth derivative is equal to 56 over 81 absolute value x to the 10 thirds. Now, this is going to be something that is decreasing. We care about this on the interval from 0.8 to 1.2. And ask yourself on that interval, can you conclude something about what's happening with the absolute value of the fourth derivative? Well, this, as x gets larger, the denominator gets larger, so this thing is decreasing. It is largest at the left endpoint. So what that means you can say is that the absolute value of the fourth derivative on this interval will be less than or equal to 56 over 81 times 0.8 to the 10 thirds. And this is the number that you use for the m. If this fourth derivative had been an increasing function, then it would have had the largest value at the other endpoint. And usually for the questions you're going to get, it should be pretty obvious if the function is increasing or decreasing on your interval. Okay, so we know so far, we know that m. Now the next thing is, what about x minus 1 to the fourth? What can we say about that? Well, we know that 0.8 is less than or equal to x, which is less than or equal to 1.2. And taking away 1 everywhere, that's the same thing as saying negative 0.2 is less than or equal to x minus 1, which is less than or equal to 0.2. And if x minus 1 is in between positive and negative 0.2, the absolute value of x minus 1 is less than or equal to 0.2. So we're going to input this and input that. So the absolute value of the remainder is less than or equal to 56 over 81 times 0.8 to the 10 thirds power. That's my m. X minus 1 is less than 0.02 or 0.2, so that's 0.2 to the fourth over 4 factorial. And that is about 0.0000967. So your remainder or your error is less than that number. This is like a worst case scenario. In the worst possible case, your error could be that much, but in actuality, it might be less. So the two things you have to figure out to do this are a number to be your m, that's the first thing. And then also figure out, based on your interval, what does x minus your a have to be? The reason I took away 1 here was because I had x minus 1. Had that been x minus 2, you'll take away 2. So those two things are what you have to figure out to get an estimate using Taylor's inequality. Okay, let's approximate sine of x at pi 6 with a Taylor polynomial of degree 4. And then we'll use Taylor's inequality to estimate the accuracy of the approximation when we have the interval, when we're on the interval from 0 to pi thirds. Okay, so we're going to need 4 derivatives. So original function is sine of x. Plugging in pi 6, we get 1/2. First derivative of sine is cosine. Plug in pi 6, you get root 3 over 2. Second derivative is negative sine. Plug in pi 6 and we'll get negative 1/2. Third derivative is negative cosine. And plug in pi 6, we're going to get negative root 3 over 2. And the fourth derivative is positive sign. And inputting pi 6, we have 1/2 again. All right, so our fourth degree Taylor polynomial will be 1/2 plus root 3 over 2 times x minus pi 6, our a value is pi 6, minus 1/2 times 1 over 2 factorial, x minus pi 6 to the second, minus 1 over 3 factorial, root 3 over 2, x minus pi 6 to the third, and finally 1/2 times 1 over 4 factorial, x minus pi 6 to the fourth. All right, let's estimate the accuracy of this approximation. So using Taylor's inequality, we know that the remainder for this Taylor approximation is less than or equal to sum m over 5 factorial x minus pi 6 to the fifth. Okay, where somehow the absolute value of the fifth derivative is less than or equal to sum m. So first let's figure out that m. So the fifth derivative is cosine. And on the interval from 0 to pi thirds, the largest value cosine takes on is 1. So the fifth derivative is less than or equal to 1. We take m equal to 1 in this case. All right, now we need to figure out what about that x minus pi 6. Well, we know we have the interval 0 is less than or equal to x, which is less than or equal to pi thirds. Taking away pi 6, that gives us negative pi 6 is less than or equal to x minus pi 6, which is less than or equal to positive pi 6. Or in other words, the absolute value of x minus pi 6 is less than or equal to pi 6. So inputting all this information, the absolute value of this Taylor polynomial's remainder is less than or equal to 1 over 5 factorial times pi over 6 to the fifth, which is about 0.000328. Next, we're going to use this result to estimate sine of 38 degrees correct to 5 decimal places. So sine of 38 degrees. So the first thing is that you need to convert that 38 degrees into radians. So 38 degrees times pi over 180. It's the same thing as 38 pi over 180, which is 19 pi over 90. And so to estimate 38 degrees, we're just going to input this value into your Taylor series. So we have that sine of 38 degrees is about equal to t sub 4 with 19 pi over 90 plugged in. And that should give you about 0.61566. Now, one question is how do you know that this is correct to 5 decimal places in the first place? Because our remainder estimate really only had accuracy to 3 decimal places. And So remember that we knew that the absolute value of r sub 4 of x is less than or equal to 1 over 5 factorial times x minus a number a to the 5th power. So using the fact that the a is pi 6 and that the x that we specifically care about is 19 pi over 90, we can say, well, for that specific value of x, this remainder is less than or equal to 1 over 5 factorial times 19 pi over 90 minus pi over 6 to the 5th. And it turns out that 19 pi over 90 minus pi over 6 is the same thing as 2 pi over 45 to the 5th power. And so for this specific x, the remainder is less than or equal to 0.000000044, which is definitely 5 places of accuracy. So the point is that this value, 19 pi over 60, was pretty close to pi 6th. And this remainder estimate that we found right here is sort of like a worst case scenario for numbers that might be closer to 0 or pi thirds. So you can expect that 38 degrees would be pretty accurate, as 38 degrees is awfully close to pi 6, because pi 6 is 30 degrees. So what we're going to do next is we're going to use Taylor's inequality to figure out how many terms we need for the Maclaurin series for e to the x to make sure that our estimate for e to the 0.1 is accurate to within 0.00001. So we know that the absolute value of the remainder from Taylor's inequality is less than or equal to some number m over n plus 1 factorial x minus a to the n plus 1. And in the case of a Maclaurin series, and this is also where the absolute value of the n plus first derivative at x is less than or equal to m. So in the specific case of Maclaurin series, we know that a is 0. And since we have e to the x, we know that the derivative of e to the x, the n plus first derivative, will be e to the x. This will be less than or equal to e to the x over n plus 1 factorial x to the n plus 1. And since we're estimating e to the 0.1 and we're using a Maclaurin series, the values of x's we care about will be x's between 0 and at most 0.1. And on this interval, e to the x is increasing, so it's largest at the value of 0.1. So this remainder is less than or equal to e to the 0.1. And we can take x equal to, well, the 0.1's the biggest, so to the n plus 1, all over n plus 1 factorial. And we want this to be less than 0.00001. And you test n's until you get a true statement, and n equals 3 is the first number that works. And the reason is when you input n equals 3, the value that you get for this expression is you find that the absolute value of R3 with 0.1 plugged in for x well, that's less than or equal to 0.0000046. So you only would need 3 terms of the Maclaurin series to have this level of accuracy. So a similar type question, but it turns out we won't have to actually use Taylor's estimate here. We can actually just use an alternating series estimate. So how many terms of the Maclaurin series for ln of 1 plus x do you need to estimate natural log of 1 plus 4? So first of all, the series for ln of 1 plus x is the sum from n equals 1 to infinity, negative 1 to the n minus 1, x to the n over n. And natural log of 1.4, well, that's the same thing as 1 plus 0.4. So this is the series with 0.4 plugged in for x. So that is the sum from n equals 1 to infinity, negative 1 to the n minus 1, 0.4 to the n all over n. That should not have been a factorial, so x-nay that. Okay, now we're going to use the alternating series test remainder theorem because we have an alternating series. So we know that the absolute value of the remainder is less than or equal to the n plus first term, ignoring the negative 1 to the n. And the n plus first term here is 0.4 to the n plus 1 over n plus 1. And we want to find an n so that this expression is less than 0.001. When you input n equals 5, that's the first number that I found that works, you get 0.4 to the 6th over 6, which is 0.0007. That's the first number first time you get something that is less than 0.001. So you need the first 5 terms. And so up to n equals 5, if you use those first 5 terms, you see that ln of 1.4 is about equal to, first term is 0.4, the second term is minus 0.4 squared over 2, plus 0.4 cubed over 3, minus 0.4 to the 4th over 4, plus 0.4 to the 5th over 5. And that's about equal to 0.33698 versus what I got in my calculator. I got that the natural log of 1.4 was about equal to 0.3364722. And look, you got these 3 decimal places matching with just 5 terms. And if you could imagine, if you did say like 10 terms, you might actually get enough accuracy that you don't need anything else and it's just good enough. Use the alternating series estimation theorem or Taylor's inequality to estimate the range of values of x for which this approximation will have an error less than 0.005. Now here, I can see that this is obviously alternating, and in the case when you can see something as alternating, the alternating series estimation theorem is quite a bit easier, so let's just use that. So by this alternating series, we know that the error is less than or equal to the next term that you leave off, which would be the absolute value of x to the 6th over 6 factorial. We want that to be less than or equal to 0.005. Well, multiplying 6 factorial over, we have the absolute value of x to the 6th is less than or equal to 6 factorial times 0.005. Or the absolute value of x to the 6th is less than or equal to 3.6. And then 6th rooting, we have the absolute value of x is less than or equal to 1.23799. So as long as x is in between negative 1.238 and positive, we'll say 1.238, as long as your x is in between those values, using this estimate for cosine will have an error less than 0.005. It's been a long and challenging unit, and that is the last lesson. You'll have to learn something new for a little bit. So take a deep breath and study for your test.